Hi, this is a talk for fractional online stochastic matching via fine-grained offline statistics. I'm Hongxun Wu, and this is joint work with Zhihao, Gavin, Tang, and Jinzhao Wu. Let us first introduce the basic concepts. The problem we're studying is online stochastic matching. This problem was first studied by Feldman, Mehta, Mirkny, and Mutikrishnan. The input is a bipartite graph G. All the vertices on the left-hand side are offline vertices. This is a set L. And all the vertices on the right-hand side are online vertices. This is a set R. Upon the arrival of the jth vertex, the set of its neighbors is sampled from a distribution dj. This set tj is called the type of the online vertex j. And this distribution dj is a distribution over all subsets of L, and this distribution is known up front. For example, here there are two offline vertices, U1 and U2. When the first online vertex arrives, we see the realization of T1. It contains U1 and U2, so 1 is connected to both of them. Then the second online vertex arrives. In this realization, T2 only contains U2, so there's no edge between U1 and 2. When each online vertex arrives, the algorithm must decide irrevocably whether to match that online vertex and which offline vertex to match it with. In the unweighted setting, the goal is to maximize the cardinality of the matching. In the vertex-weighted setting, the goal is to maximize the total weights of all matched offline vertices. Namely, all the offline vertices are weighted and all the online vertices are not. This makes sense, for example, if offline vertices are items that you want to sell, and online vertices are arriving customers, then naturally you would like to maximize the total price of the items being sold. In online algorithms, the usual metric is competitive ratio. In this case, it is the expectation of the value achieved by the algorithm divided by the expectation of the value achieved by the offline optimum. When all online vertices are identical, namely they all have the same type distribution dj, we call this case ID arrival. In this ID case, the optimum ratio is achieved by Huang and Shu, and they gave a ratio of 0.711 in the unweighted case and 0.701 in the vertex-weighted case. The previous literature mainly focused on the ID case. For the non-ID case, the best algorithm is still the 1-1/E competitive algorithm by Agua, Go, Current, and Mehta. Our contribution is a new framework for studying online stochastic matching. For ID case, we proved a ratio of 0.704 for vertex-weighted case, which slightly improves over the previous algorithm. And one good thing about our algorithm is that it also works for non-ID case. It achieves a competitive ratio of 0.666, and it is the first algorithm breaking 1-1/E for the non-ID arrival. Parallel to our work, Huang, Shu, and Yan also improved the ratio for the ID case. They got a better ratio of 0.716 for vertex-weighted setting. Now let's explain the key idea of our framework. As a warm-up, let's first look at a simple one-choice algorithm and prove that it is already 1-1/E competitive. When an online vertex J arrives, we first sample exactly one neighbor of it. Each neighbor U is sampled with exactly this probability, namely the probability that J is matched to U in the offline optimal matching, conditioning on the neighbors of J. Then we try to match J with this sampled neighbor. If this neighbor is already matched, then we would fail. Then if we fail, J would be unmatched. If we take the expectation over Tj, we can see that each Uj is tried with probability Puj, which is the probability that J is matched to U in the offline optimum matching without fixing Tj. Then for each offline vertex U, we define Pu to be the summation of Puj over all online vertices. Since U can only be matched to one online vertex at a time, these events are disjoint. So this also equals the probability of U being matched in the optimum matching. So finally, the probability of U being matched by the algorithm is at least 1 minus the probability that U has never been tried, which by simple calculation is at least 1 minus 1 over E of Pu. Since for each offline vertex U, we already know that the probability of it being matched by the algorithm is at least 1 minus 1 over E of Pu. And this probability Pu equals exactly the probability that U is matched in the offline optimum matching. We get that the expectation of the algorithm is at least 1 minus 1 over E of the expectation of the optimum. So it is 1 minus 1 over E competitive. The previous approach extends this idea to a two-choice algorithm. Instead of sampling one candidate, it samples two candidates and tries them one by one. For example, here, when the vertex 3 arrives, we sample two candidates, U2 and U3. And then, since U2 is unmatched, we just match 2 and 3 and we don't have to try U3. New arrived vertex J would be unmatched only if both candidates are already matched. So our key idea is to apply the multi-way online selection algorithm developed by Gao et al. And Blank and Charikar. This algorithm, instead of having two candidates, it has all n candidates. And that's where the improvements come from. Parallel to our work, Hongxun and Yan also exploit the power of multi-selection by incorporating the multi-way online selection techniques in their algorithm. So now let us introduce our framework. Our framework views multi-way selection as a rounding scheme for fractional matching problem. In fractional matching, upon the arrival of each online vertex, the algorithm matches it with each offline vertex U with a fraction of YUJ satisfying the following constraints. So first, these YUJs should be positive and the summation over all offline vertex U should be less than 1. Second, when there's no edge between U and J, YUJ has to be 0. And this is equivalent to U not in Tj implies YUJ equals to 0. For example, here, there's no edge between U3 and 1, so Y31 has to be 0. And then the second online vertex arrives, again, this 3 has to sum up to at most 1, and Y12 has to be 0. Now we start defining the weight of a matching. For each offline vertex U, we define YU to be the summation of YUJ over all online vertices J, namely the total amount of fractional matching that U receives. The weight of fractional matching is defined as following: the weight of U times how much U is matched summed over U. Note here, when YU is larger than 1, then U is fully matched, and it only counts as 1. Now we move on to explain different rounding schemes for fractional matching. The simplest one is independent rounding. This is similar to what we have seen in the previous one-choice algorithm. For each online vertex J, you just independently sample one neighbor according to the probability YUJ for different U, and then you just try that one neighbor. Note when YU equals 1, this gives you exactly 1 minus 1 over E. So intuitively, to break 1 minus 1 over E, you have to use a better rounding scheme. The other rounding scheme is the multi-way selection algorithm that we mentioned before. This is called the online correlated selection. For each J, among all its neighbors, with YUJ larger than 0, it selects 1 to match with. And this selection choice is based on the previous choice that it has made. so its selection are negatively correlated for different online vertex j. It can achieve an improved bound over the independent selection. In conclusion, we define yu to be the total amount of fraction that u receives in the algorithm. The performance of the fractional matching is w times fyu summed over all offline vertices u, with f equal to minimum of 1 and yu. This is the ideal case as if these trials received by the offline vertex u are completely disjoint events. On the other side, you have independent rounding, for which these trials to u are independent events, but they are not disjoint. You get a worse bound which cannot break 1 - 1 over e. In the middle, you have online correlated selection. Its selections are negatively correlated, so it improves over the independent rounding scheme. Now we are ready to present our algorithm and point out the main difficulty. In our algorithm, we mainly focus on a special class of fractional algorithms using estimators. For example, we have seen these estimators yuj in one-choice algorithm. We call these estimators independent estimators because it only depends on the type of j but not on the type of other vertices. So for different online vertex j, these yuj's are independent. In our algorithm, we only consider these unbiased estimators that we will define now. So first of all, these estimators can only depend on the types of already arrived online vertices, so that we can compute their value in our algorithm. Then they are unbiased if and only if, first, for each online vertex j, the summation of yuj over offline vertex u should be less or equal to 1. Second, if there's no edge uj at all, yuj should be 0. These two guarantees that the estimator can fit into our framework. Finally, yu, which is the summation of yuj for a fixed offline vertex u, its expectation has to be the probability of u being matched in the optimal offline matching. This is why we call it unbiased estimator. It is easy to see that the independent estimator satisfies all these three requirements. For any unbiased estimator, if the expectation of fyu is larger or equal to mu times yu, we can prove that it is mu competitive. The proof is very simple. Since the performance of the algorithm is fyu times wu, sum over all offline vertices u, and we know that the expectation of fyu is at least mu times the expectation of yu, which by the unbiased property of the estimator, we see that it equals the probability of u be matched in the offline optimal matching. So we get that the performance of our algorithm is at least mu times the expectation of the offline optimal matching. However, it can be hard to prove this inequality. For example, let's consider the fractional matching. So fy equals the minimum of 1 and y. We do know the expectation of yu is between 0 and 1. And for any deterministic y in 0 and 1, we have fy equal to y. So it seems like it's hopeful to get mu equal to 1. However, here yu is a random variable, and in some realization it can be larger than 1. Therefore, it can be hard to prove a bound on mu. Let me explain this. First, the function f is concave, and suppose yu is with half probability 0.2 and with half probability 1.5. By Jensen's inequality, you can see that the expectation efyu is much smaller than eyu. This is because the 1.5 part contributes much less to the left-hand side than its contribution to the right-hand side. The same thing also holds for the other two functions because they are all concave. So intuitively, by distance inequality, the more spread out these points are, the larger loss we get. So we must bound the spread of these random variables yu, and this is the main difficulty in this approach. Now we're ready to present our algorithm for IID arrival. For IID arrival, our approach for bounding the spread is by bounding the variance of yu. Then we can solve an optimization problem to find the worst loss given the variance bound. Namely, we find a constant mu sigma f such that for any random variable with variance bound sigma, we have that EFYU is larger or equal to mu times EYU. Then the problem is reduced to design the unbiased estimator with minimum variance. So what are the candidates? We have already seen the independent estimator. It only takes Tj into account and resamples the type of all other vertices. We can also define fully correlated estimator, which takes the whole history into account. In the middle, we can define a windowed estimator of window ij. Instead of looking at the full history, it takes the history up to vertex I into account. So it implicitly resamples all the types before I. And this is the definition. It's the probability of uj in the optimal matching conditioning on ti all the way to tj. So which one is better? To answer this, we first divide the second moment of yu into products of yuj and yuk for all online vertices pairs j and k. By the definition of unbiased estimators, the expectation of yu is always the probability of u being matched. So bounding the variance is equivalent to bounding the second moment. Intuitively, yuj must take tj, which is itself, into account. If yuk also takes tj into account, then let's see what will happen. When there's an edge between u and j, namely u is in tj, then yuj will be larger because the edge uj now has the probability of being matched. In contrast, yuk will be smaller because now the edge uj exists. This will decrease the probability of uk being matched in the offline optimal matching. Therefore, we get negative correlation between yuk and yuj, which is great because it decreases the second moment. On the other hand, if yuk and yuj both take a previous ti into account, like this, then when the edge ui exists, namely u is in ti, both the probability of uk being matched and the probability of uj being matched in the offline optimal matching will decrease. So both yuk and yuj will be smaller. This is bad for us since it introduces positive correlation and increases the second moment. So as a result, a longer window length for yuk would cover more of such tj, and it will introduce more negative correlations for k. However, it will also create more overlaps between these windows and introduce positive correlations. So there's a subtle trade-off between them. So the fully correlated estimator, which takes the whole history into account, is not the best estimator. One can observe that the mixing of unbiased estimators is still an unbiased estimator. So finally, the estimator we are using is a mixing of windowed estimators. It gives each window a weight of beta over n and gives all the remaining weights to the fully correlated estimator. And finally, we optimize over beta and find out that beta equals 0.79 is the optimized constant. And finally, we briefly introduce our result for non-IID arrival. In this case, we consider independent estimators, and we were able to characterize the worst-case arrival for independent estimators. Then we find out that surprisingly, under such a rival, all other unbiased estimators simply degenerate to independent estimator. So in a certain sense, in the non-IID case, independent estimators are optimal. And this is the end of our talk. Thank you all for listening.